47.
Okay. Determine the number of electrons for the following quantum numbers. So let's do, I have written for the following quantum numbers, let's do n equals 4 and L equals 2. So how many electrons can exist for the principal quantum number equals 4 and the angular number equals 2? My brain is like slowly shutting down. Like the brain fog is starting to come in so bad right now. So for L equals 2, this is a d orbital. Every d orbital can hold 2 electrons, and we have 5 of them: dxy, dxz, dyz, dx squared minus y squared, and dz squared. So if we have 5 orbitals and each can hold 2, then the number of electrons we can hold is simply 10 electrons. All right, let's do another one. What about n equals 4? L equals 4, and m sub L equals plus 1. How many electrons can you hold in here? The answer for this is 0, none. Because, remember, our L has to be less than n. This is a rule. It cannot be equal to n, it has to be less than n. So what we're saying here is that 4 is less than 4, which is not true. So there are 0 electrons for this set of quantum numbers. This orbital just doesn't exist. All right, let's look at n equals 3, L equals 1, m sub L equals 0, and m sub S equals 1/2, plus 1/2. Let's push this down. So whenever you're given a set of quantum numbers, and then the very last one you're looking at m sub S of 1, we're only looking at 1 electron because it's giving you the specific spin of that electron. So don't even worry about all this stuff. If you read it, you get to m sub S and it says plus 1/2, oh, well, then it's just 1 electron. We're just looking at 1 electron. If I remove this, so now the set of quantum numbers are n equals 3, L equals 1, m sub L equals 0, then now we're looking at a specific orbital, only 1 orbital, which can always contain 2 electrons, so then the answer becomes 2 electrons. But because we were looking at an m sub S value of plus 1/2, we're only looking at just 1 electron. Let me see, is there anything else I should go over for quantum numbers? I don't think so. I think I'm going to draw an orbital also. I don't have a question for drawing an orbital, but I'll definitely draw one. I have questions about that. Okay. All right. Determine the following element or electron configuration. No. I'm sorry, I'm keeping you here, Dan.
Yeah, that's fine.
Let's do barium. Let's determine the electron configuration for barium. And let's do the noble gas configuration, so we have like this really long thing. So if we go to the periodic table, I'm going to zoom in a little bit so we can actually read it. Yeah. Hey, I get to use my pointer. So barium's right here. This thing is so awesome. The noble gas before barium, I want the whole periodic table, please.
There you go.
So barium's right here. The previous noble gas is xenon. So we're going to write open bracket xenon. Go back to our periodic table. Barium has the principal quantum number of 1, 2, 3, 4, 5, 6. So it's going to be 6s. And it's right next to cesium right here. So it's 6s, 1, 2. 6s, 2. Done. Finished. Oh god, do I have to write all of that now? Next one. I'm not going to go forth. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. What element has the electrical configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4fp4? So, go back to our periodic table. So we're stopping at 4p4. Our d orbitals start at 2p. So this is the 2p, 3p, 4p. We have 4p4, so it's 1, 2, 3, 4. So we're left with selenium. You could also read, like, as you're reading the entire electrical configuration, you can go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, D starts at 3, 3d10, 4p, 1, 2, 3, 4. I love this thing. It's so much fun. I'm so glad Nat gave me this. It's awesome. So the element we have for that is going to be selenium. So this is selenium. What else do we have? The next one is gold. Oh, this one's great. Gold is a great example. So gold is located in the transition metals. It's right here. It's element number 79. The previous noble gas is xenon. So let's write down, open bracket, xenon. Go back to this. Close that. So see, we have xenon. We go down here. We have, let's see, 1, 2, 3, 4, 5, 6. So this is 6s2. So we're going to go 6s2. Then we're going to go to the lanthanide. So before we fill any of these d electrons, we have to go through all of this entire row right here before we continue back on into the d block. So we have 6s2, 4f14, because 4f14 starting with cerium. You don't start, lanthanum is considered a d block. So we consider this as d1. It's just sometimes the periodic table likes to write lanthanum down here. Sometimes it likes to write it up here. It just so happened that this periodic example has it written down here with the F block. So we consider this a D1, so we're not going to count this one as our first F electron. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So full F block. Then we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would have xenon, 7s, oops, sorry, 6s2. 6s2, 4f14, 5d9, except gold is an exception. So if you remember when I talked about exceptions, gold is under, if you look at our periodic table, gold is in our copper column. And we said that whenever we write the electron configuration for any of these metals, what happens is one of these electrons in the s orbital decides it is a lower energy configuration for me to go from this orbital to this d orbital, because it'll give me a noble gas-like filled shell. So we're going to remove one of these electrons from the 6s2 orbital. So we're going to be left with 6s1, like this. We're going to demote him to 5d10. Remember I said when you have a filled shell it acts noble gas-like. And so this would be the electron configuration for gold. All right. Last one. And then we'll draw we'll draw an orbital really quick. Rn. 7s2. We have radon 7s2 61 5f3. This is going to be an element in the lanthanides and actinides. This is a lot easier than you think it is. You're looking at this and you're like, but what about all these exception rules that we're not supposed to know for the lanthanides and actinides? You're not supposed to know them. You can answer this question without even bothering looking at the exceptions. Simply, what you do is you add up the atomic numbers. The atomic number of radons can be equal to the number of electrons. And you add up these number of electrons, and that number that you get out of it is going to be the atomic number for the element you're looking at. So radon, in the periodic table, has, get the stick, Jake, get the stick, has an atomic number of 86. So we're going to write down 86 here, plus 2s electrons, plus 1d electron, plus 3f electrons. This is going to give us 86 plus 2 is 88, 88 plus 1 is 89, 89 plus 3 is 92. So if we go back to our periodic table, we find the element that has the atomic number of 92, we get uranium. That's the element we're looking at right now. So you don't have to know all these exceptions for the lanthanides, actinides. When you're given an electron configuration like that, you simply just count. All you do is just count stuff up, add it up, arithmetic, move on. That concludes examples. Now I'm gonna. You good to say if I draw like an orbital really quick?
Go for it.
Okay. Let's draw. Use black. (4d) x squared minus y squared, because it's relatively easy to draw. So before I draw anything down, the first thing I'm going to do is I want to determine how many nodes exist for this orbital. Remember, total number of nodes is equal to the principal quantum number minus 1. So here we have 4 minus 1 gives us 3 total nodes. Some of these nodes can be angular nodes, some of these nodes can be radial nodes. The d orbital, which is the 4-leaf clover, and I want the book because it's going to have good pictures of this. It better have good pictures of this. What's going to have these? Yeah. Oh man, these are nice. It's beautiful. So if we look at let's find an s orbital, which is just the sphere. Give me a little bit of. This sphere has no planes that bisect it, meaning there's no nodes for an s orbital. There are no angular nodes for an s orbital. Never, 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 never. There's radial nodes, but never angular nodes. A p orbital, which is on this page, always has one angular node. And you'll see this plane that's bisecting these two lobes. That's your angular node for the p orbital. The p orbital always has one angular node. The d orbitals have 2. So you'll notice if I could draw one node here going in this direction, and then I could draw the next node going in this direction. Here we have 1, 1. Again for the dxz and the dyz. And then for the dz squared, we can imagine one giant cone would be one node, and then the next giant cone would be the next node. So we know for a fact that for this d orbital, we will have 2 angular nodes. The leftover, because we have 3 total nodes, the leftover node is going to be a radial node. So I'm going to draw my Cartesian coordinates in black. And you don't have to, obviously you don't have to draw your orbitals in color in the test. You just have to be diligent. I'm going to draw the Cartesian coordinates in black, and I'm going to draw the angular node in, I want to use blue and red for phase. I'll pick another color here. Where's purple? Yes. All right. All the pins I want. So this is y, this is x. The dx squared minus y squared is going to have the lobes along the axes. And so our angular node is going to be bisecting these two axes. Here's our first one in green. And then here's our second one. Just like. So these are the angular nodes. The radial node, the leftover from our total node, I'm going to draw it in purple. Radial nodes are circular. They're just giant circles. So I'm going to try to draw a circle. Yeah, that's not that bad. All right. Okay. Now we're going to draw our lobes. So we have, it's a 4-leaf clover, so we're going to have one lobe here, one here, one here, one here, giving us 4. It doesn't matter which phase you start with, as long as whenever you cross a node, you change phases. So I'm going to start with red over here, and I'm going to move along the x-axis this way. And every single time I cross a node, I'm going to change color. So let's do like this. Fill it in. I'll be an artist. Be an artist. Yes. Dan's like laughing over there, like really. I'm going to cross this radial node right here. So when I cross over, I'm going to change phases. So now it's going to be blue. And here's the trick. When you cross the origin here, you're not crossing one node, you're crossing 2 nodes. So you're crossing the one node that's in this, the one angular node that's like this, and then you're crossing the other node that's like this. So because you cross it twice, whenever you cross an even number of nodes, the color does not change. The phase stays the same. So you'll notice that when I went to red to blue, I crossed one node, which is an odd number, which means I have to change colors. But because I'm crossing 2 nodes here, the blue stays. Well, I didn't write down purple was the radial node. So let's put it right here. Radial node. And now I'm going to change colors to red because I'm crossing this radial node again. So I'm hopping over that line. That looks disgusting. Come on. That's fine. So that's to the cloves. I'm going to do along the y-axis now. So the phase, I'm going to start from down here and I'm going to move up. If I were to travel from this lobe and go in this direction, I cross one node, one angular node. So the color of this node has to be different from this one. So we're going from red, crossing this node, and starting with blue. And in your exam, to denote shade the node phase, you can shade a lobe in and leave one lobe unshaded, or you can use pluses and minuses. So you can do plus, minus, minus, plus, etc., etc. We're going to cross this radial node, which means we're crossing one node, so we're going to change colors again. Crossing two nodes, the two angular nodes, so our color stays the same. And then finally crossing the last node to give us blue. This would be the answer for a dx squared minus y squared. Notice that it is not a 3D picture of this, it's a cutaway. So it's as if I took the orbital and I sliced it in half and I'm looking at it like Jawbreaker style. So you don't have to be three-dimensional, don't get all like artistic and stuff, just like literally imagine you take the orbital and you just like guillotine it, and you're just looking at just the face of it. I'm done. It's good enough.